All right, today's problem is, which is our last tree problem, is serialize and deserialize binary tree, which is a really fancy way of saying turn a tree into a string and then turn a string back into a tree, the same tree. Okay, but let's take a look at their prompt just to dissect it a little bit. So the prompt says implement an algorithm to serialize and deserialize a binary tree. And they give us a few more details here. Serialization is the process of converting an in-memory structure into a sequence of bits, or characters in our case, um, so that it can be stored or sent across a network to be reconstructed later in another computer environment. And then it says you just need to ensure that a binary tree can be serialized to a string, and then that string can be deserialized to the original tree structure. There's no additional restrictions on how your process should work. And they tell us, by the way, the format below is sort of the standard for how NeetCode does it, but we don't have to do it that way, basically. Okay, so for example, with this tree here, well, it's not especially interesting as far as the input and the output because they should be identical, right? So the idea is if they're going to give us this tree, we're going to turn it into a string and then turn that string back into a tree, and it's going to compare the original with what we get and see if they're the same. So you can see that they're identical, which is what we want because we're trying to recreate the same tree, right? Or the same structure at least. Wow, that's very Ship of Theseus. Like if you serialize the tree and then deserialize it and reconstruct it, is it still the same tree? Hmm. Anyways, so it should be identical when we've done the serialize function and then the deserialize function, we should get something with the exact same structure. They give us one clarifying example here to say, hey, by the way, if it's an empty tree, we should still have an empty tree when we're done. And then they tell us for the constraints, the number of nodes in the tree is between 0 and 1,000, so there could be no nodes. There could be up to 1,000 nodes. The values will be between negative 1,000 and 1,000. So again, no unreasonably large numbers here or nothing that will overflow for us. And yeah, there's lots of ways to do this one. I'm going to share the one that I think comes to mind first for me, but I first wanted to touch on the fact that this is pretty similar in nature to, I don't think yesterday's problem, but 2 problems ago, which was construct binary tree from pre-order and in-order traversal. So if you know how to do this one, you could just create a pre-order and an in-order traversal, send that as your serialization, and then use the solution to this problem to deserialize. But we'd like to be able to do it, so that's one way to do it. We've already covered this problem before, so I'm not going to say let's do it again. You know, if you want to know how to do it with both traversals, you can refer to this problem's video. But for today's problem, we're going to try and do this without needing 2 traversals. We want to just traverse the tree once and encode it, and then be able to traverse that encoding and decode it, right? Okay, so I'm going to kind of jump straight to the thing that lets us do that with one traversal here. And in fact, maybe we'll use, it doesn't super matter what tree we use, but maybe we'll use this one just because it's here. This was the one that we used for the in-order, pre-order traversal. And you'll notice, if you take a look at the work that we did down here, one of the things that those traversals did not do, which is customary and normal, also I forgot to open chat, so sorry. General body meeting will be happening today. There unfortunately will not be food, sorry. But we will be in the spa building at 7. Yes, okay, so yeah, sorry. Ordinarily we have food at like all of these things, but I don't know, we just never really did for GBMs.
Yeah. Oh, we did
Um,
once.
yeah, we did once for the GBM. If you come to the GBM, I've got a little time after I gotta eat. I would love to buy you dinner. Open offer. Anyways, um, so yeah, for the previous problem, we did pre-order and in-order traversals here. One of the things that we did not include in these traversals was the none nodes. So there was no indication in the actual traversal of like where the tree stopped, right, or where the subtree stopped. So we had to figure out on our own, hey, this is the left subtree, this is the right subtree, right? Um, so we have a few options as far as how we want to handle this. Um, but in short, if we were to add the none nodes in here, so like this guy right here could be followed by, well, I don't remember the exact structure, but so like the one could be followed by a 4, and the 4 could be followed by a none and a none. And then we could have another none out here to indicate that this is the whole length of this subtree right here. Yeah, anyways, in short, if we included the nuns strategically here, we actually could encode this whole thing just in one go. And we wouldn't need two goes, and we wouldn't need to decode using both traversals here. We could just do it all at once. So that's the core of what we're going to do. Let me paste this here, and then we'll get rid of some of the encodings. And then we'll talk about how to do this all at once. So the core idea, again, is if we include the none nodes, we can be a lot smarter about how we encode and how we decode. So we'll go ahead and do this. I don't think it matters which traversal we do, but I'm going to say we'll do it as a pre-ordered traversal. And what I mean by that is we're going to handle the self node first, and then we will handle the entire left subtree, and then the entire right subtree. So we'll actually talk about this at the GBM a little bit. But when we say pre-order, that means handle yourself first, basically. So self, followed by the left subtree, followed by the right subtree for every single node in this entire tree. Okay, so we're going to do this, but we're also going to include the none nodes. So if we do this traversal here, we're going to do self first. So this will be, in our traversal here, we'll have 3, and then we'll go left. And this guy, we're going to handle yourself first, which is 1. And then we're going to go left. And then you're going to handle yourself first, so we get a 4 here. And then you're going to go left, and there's nothing there, so we actually will write a none for that entry. Okay, so now for the 4, the left subtree is done. So we've done self, we've done left, now we're going to do right. And that's also a none. So that will unfold here. And now the 4 is like completely handled. We've done that whole subtree, right? Okay, so we wrap up one more time. We're done with the left subtree. I guess I should have put left on all these to indicate we started. Anyways, so we do the whole left subtree, and now we can say, let's do the right subtree. We put another none in the list. Wrap that back up, and now the whole right subtree is done. Okay, wrap that whole side up, and now we're ready to start handling the right subtree of the root. And yeah, same thing. We get here, handle yourself, that's a 2. Handle your left subtree. Okay, so we get here, handle yourself, that's a 6. Handle your left subtree, that's a none. Okay, wrap that back up. Now that you've done the self and the left, you can do the right subtree, which is a none again. Okay, wrap that up, wrap that up. Now we're ready to do the right subtree. Okay, so I'm gonna speed this up a little bit because I'm sort of repeating myself ad nauseum here. Okay, so now we go right, handle yourself, now go left, handle yourself, now go left. Done with that subtree. And then now we go right. This is way longer than I thought it would be, I'm not gonna lie. Okay, we wrap that up. Now we're done with this left subtree, so we go right. And we get a none there. And now we wrap this up, and now that means this is done, that means this is done, and the whole tree has been covered, right? Oh boy, that was a lot. Okay, so this is the encoding we get right here. And basically what we can do here is every time, or we can split this up still into a left subtree and a right subtree. But the question is, like, how do we know when this subtree is done? Well, it's when we've hit like kind of a none on both sides, I guess is how you could think of it. So for any, I should say for any particular node, you'll know that you're completely done with that node when you hit 2 nuns afterwards, right? Ooh, I feel like that wasn't a good way to phrase that. Okay, here, let's think about it this way. Well, let's start with what we know. We know right here that this is the left subtree, right? And this is like, we know because we're looking at it. So how could we take this information and find out that this was how it was split? Well, it's a great question. I like know how to do this in code, and now I'm trying to think about like how to logically explain how we know that. I guess one way you could think about this is maybe you don't know it off the bat, but you can continue breaking it down. So you at least know that the next item here is the left child of the root. So like this is the absolute root. And we know that this guy will be its left child. The next thing from there, so I guess you could think of this as a stack. The next thing from there will be the left child of the left child, right? Wow, how best to phrase this? I'm like, I want to try and describe these as a better way than just left. It's like the root, and then the root's left, and then the root's left's left. You know what I mean? um, yeah, I think that's about the best that I can do with it. Yeah, you know what? Okay, here, let me think about it this way. By the time we get to the second node, we know that the left subtree begins here. We don't know where it ends yet, right? But we at least know that this is like the left child right here. And within this layer, so actually let me use some colors here. So we have the root, and we now know that the root's left subtree begins here. And we can repeat this process. Let's think about, okay, now that we know that we're looking at a subtree, let's call this the root now in orange. Okay, we know that this guy's left subtree starts right after, right? Okay, and then one layer deeper here, we've got the yellow root right here, and we know that the yellow root's left subtree starts right here. Okay, it's at this point that we can begin to kind of unravel. We know that, or since the next node is a none, we know that there isn't a left subtree, right? It's just empty. And then the next node we look at, that's a none again, and since we've hit two nuns in this layer, I guess is the way to think about it, that means that we've finished, right? Okay, actually, hold on, I lied. I've been saying left subtree, which is correct. Since we hit a none, that means that this subtree is complete, right? So this is the yellow subtree's left node. And then we hit another none, which means that this is the yellow subtree's, the yellow subtree's right node, and it's just a none, right? Okay, now that we've exhausted the left and the right subtree for yellow, we know that that's actually the end of the left subtree for orange. Oh, that was such a complicated way of explaining it, but this is the core structure that we're going after, right? Is if your next node is a none node, that's the whole subtree right there, right? So for the yellow part right here, we hit none on the left, which means the whole subtree is empty. We know that that's the case. That's just how none nodes work. Okay, then we look at the next node. Well, that's none as well, which means the whole right subtree is empty. Okay, and since we've now completed the whole right subtree, that means we've completed like the entire section there. And since we've completed the entire section, we now know that the left subtree of the orange is done, right? And then we repeat. At this point, we go, hey, this orange, we know we're done with the left subtree. We just hit a none for the right subtree. So let me say, I guess this is left right here, and this is right. Now that we've exhausted the left and the right subtree, we actually know that that whole thing is done, right? So now we can go one layer out and say, hey, since we just finished with the whole left subtree of the white layer, we know that the next node is where the right subtree starts. And you can see this is like reflective of the overall structure, right? Oh boy, what's going on here? I hope that like even vaguely explained. I feel like I'm not doing awesome at this. And I think this will connect well to the code, but this is the overall idea is like you can just go node by node, and as you go node by node, you'll find out where each individual subtree ends once you've done the root, the left, and the right subtree, that means you're done with that whole section, right? Okay, great. And this isn't actually completely true because or I shouldn't have circled that white part because the white part is actually going to encompass the entire like thing here, right? So you can tell diagrammatically that this is just, we've only found the root and the left subtree. You've still got to find the right subtree, right? Since we just finished with the left subtree, we know that the right one starts right here, and now we can kind of rinse and repeat. So this, we'll call this the green root right here. And we know that the next node is the beginning of its left subtree, right? Okay, so one layer deeper here, this guy's the blue root. Okay, we hit a none node for the next guy, which tells us that's the whole left subtree. And then we hit a none node for the next guy, and that tells us it's the whole right subtree. So we know that this section right here is complete. The blue node is done. And that was this right here. Okay, and since that just wrapped up, that means this was the end of the left subtree for green. And since we're done with that, now we know that the next guy is going to start the right subtree for green. Okay. And okay, actually, no, we have to wrap it up first. Okay, so 7, we'll call this the purple root. And since we know that that guy's the root, that means that the left subtree is going to start right here. And that will be its own root, which I'll call the pink root. Dear God. Okay. And again, we hit this same situation where we hit none, and that tells us that the left subtree is empty. We hit none, that tells us that the right subtree is empty. Okay, and since the left and the right have wrapped up, that means that this guy is also now wrapped up, and it's the left subtree of purple. And then finally we hit another none here, and that tells us that it's the right subtree of purple. Oh, and now that purple has found its root, its left subtree, and its right subtree, this means that green is now wrapped up. And this whole section right here represents its right subtree. And since green wrapped up, then we can go one layer up and say, hey, this means that white is now completely done. And this represents its right subtree. Oh my gosh, that was so much talking. And low-key, this problem is easier than that. Like, this did not require all of that, which is crazy. But anyways, 5 was the pink subtree here. So just to complete our diagram, this is 5. This was purple right here. Ooh. Hello. There we go. And then this, wait, green is not done yet. Green was this whole thing. And then white is the whole damn thing. I should have left myself way more space here. I didn't think I was going to do all this circling. Okay, you get the idea. Oh God, it's just getting worse. Okay, so yeah, this is way more structured than I was betting on being here, but this is the core idea. I'm going to jump over to the code, but essentially if we do a pre-order traversal and we mark down the none nodes, we can use them to smartly diagnose when a subtree is completely exhausted. Ugh. Okay. And we literally just need to go one by one, and we can complete the tree traversal here. So let me know if you have any direct questions about that. I'm going to leave the diagram up in split view, but I am going to start the code. Actually, I lied. I don't want it to look like that. Please. Please. Okay. I'm going to open this up first. And split this over here. And there we go. All right. So for the serialize part, this is actually not too bad. We actually just need to do a depth first search that goes pre-order. So I'll say, let's say def pre-order DFS. And what do we need to pass it? I think just a root, because we're traversing the tree here. And since it's pre-order, what we'll do, okay, so actually, we need to keep a list. I'm going to keep a list of values, and then we will join it together as a string at the very end. So I'll say node list equals empty list. So this way we'll just be able to refer to it. Or actually, let's say self.nodelist equals this. Oh, I hope that doesn't bite me in the butt later. I'm not 100% sure how LeetCode handles like class variables or like what it's interacting with when it gets run. So I think that should be fine, but we'll figure that out later. Okay, so since this is a pre-order traversal, the first thing we should do is handle myself, or the current root node. So I'll say self.nodelist dot append root.val. Okay, and then we need to pre-order DFS with root.left and pre-order DFS with root.right. So this is like the core idea behind a pre-order traversal. The only thing we need to do is an early exit. So if we don't have a node, then instead of appending the value, because there's no value there, we can append. I'm just going to choose like the symbol X since it's not a number. Doesn't really matter what you choose though. Dot append X. Okay, and then we want to early exit. Okay, and I think that's it. So what this will do is populate node list with all the strings that we want. And then, so we'll do pre-order DFS with root. I should probably call this node just to avoid naming collisions. So we'll call these node.val, node.left, node.right. Okay, and then what I'm going to do just to diagnose this and make sure it looks the way we want it to look is I'm going to print node list. But assuming it worked out correctly, so I'll also include the rest of it, we should be able to return, I'll say let's separate everything by a comma. I think it's like this. Oh, no. It's nodelist.join, comma. So it says, go ahead and put the list together, just separate everything with a comma. Okay, let's run this just to make sure it worked. Hello? Oh, I have to put like I'm gonna put pass here just to make it do nothing. Okay, now what's broke here? Oh, did I not? Oh. Now shouldn't that have stopped? If not, oh, so I literally said, let's not do naming collisions, and then I gave myself a naming collision. Love that. And I forgot to say self.nodelist right here. And I forgot to do self.nodelist right here. Oh, is this not the thing? I'm gonna cry. Is it comma.join? Self.nodelist. Love syntax. Love syntax. Oh, I have to cast these as strings right here because we can't join integers. This is so annoying. This is not the kind of debugging I like doing. Okay, let's see if we got what we got. Here's the list. It's, okay, 1, 2, none, none, 3, 4, none, none, 5, none, none. Let's just make sure that's what we wanted. Yeah, 1, 2, none, none, 3, 4, none, none, 5, none, none. Great. Sweet. Okay, so that's what we wanted. I'm going to assume that this worked. I should have just printed that, but oh well. Okay, so this encodes it the way we wanted it over here. And now we need to deserialize it. Okay, so this one, let's think about this. I think we want another helper function here, but we also need something to like, so we're going to do this recursively still, but we also need something to like track the node that we're looking at right now. So I'm going to say counter equals 0, I guess, and then def Um, I don't know, reconstruct. I just need a helper function here. So I guess deserialize helper is what I'll call it. Okay, and it doesn't need any information, I think, because it just needs to know what node we're looking at, and we can just let that happen by using that known local counter, which I'm going to mention right here. Okay, so what do we need to do? Okay, hold on. I'm going to just set some stuff up so we have some meaningful things to refer to here. I'm going to say, what was I thinking about? I was thinking about how we need to access this as a list rather than a string. So I'll say self dot, oh, well, we want to turn it back into a list, and we already have a node list. I think it's fine if we do this. Self dot node list equals, and I'll say now comma dot split self dot node list. I think this should work. Let's print that once again. So I'll unprint it right here, and then reprint it right here just to make sure. Uh, let's do that just to make sure this works. Ooh, okay, so that's not super nice. Codec object has no attribute node list. Well, we set it right here, but now it's not working. So again, NeetCode does some weird stuff sometimes. I'm gonna just do this. I'm gonna say new node list is an empty list. I don't want to do that either. Oh, you know what? No, I think we're fine. I think we're fine. It's just that we can't self.split node list. We're self.split data, because that's the thing that gets passed into the deserialization function. So actually, let me do this, and then we will print node list and make sure it works. Oh, not self.data, just data, because it gets passed at the function level. And then yes, I do want to print self.nodelist. Man, I'm just making 100 mistakes an hour, a minute, whatever. um, hello? Didn't we join these all together with a comma over here? Uh, hello? Let me print data here real quick. Yeah, why did that just, is that not the right syntax? Self.nodelist is comma dot split data. Is that not? Is that not what it's supposed to be? Okay, here's what we'll do. Print, comma. I should know how this works by now, by this point in my life, but here we are. Nope, it really did not like that. What? Is that not right? Okay, we're gonna look this up. Oh, split string by delimiter Python. Oh, it's string dot split. I'm gonna kill myself. Anyways, okay, so data dot split comma is what we want. Yeah, well, oh, you knew that, did you? And yet you said nothing. You hate me, for real. Okay, let's just make sure this worked right. Let's print self.nodelist. It was, well, I mean, I guess, kind of. Okay, and we got the things that we wanted. However, we want those to be integers. Oh, no, we don't. So we'll have to cast these as integers later, because if we don't, then we'll have a bunch of these that have values of integers, or strings instead of integers. So we'll remember that for later, but this did the thing that we wanted it to do. So now we need to do the deserialization. Starting from, yeah, actually we just call it. And then we're gonna return, ooh. So we're gonna get the root back from here, and we're gonna return the root. So actually we don't need to do that, we can just return what this returns. Okay. Let's now think about what we actually have to do for this. The actual problem. This is the actual problem right here. We finally got to it. So if the node that we're looking at, so this is going to be self.nodelist at index counter is x, then we can early exit. There's nothing here. It's actually the end of the subtree. We can return none. Okay, so if it's not, then what are we going to do? We need to, oh, not, yeah, actually that's fine. If that's not, so like for example, if we're at the beginning of the string here, or the list here, then we're going to create a node that has a value of self.nodelistCounter, except we need to turn it into an int. Okay, so the value will be this. The left subtree will be whatever you get when you do this again with the next node. Ooh, but we need to be able to increment the counter as we go. Okay, so we're gonna have to store this as we go. We can't return it all at once here. I'll say, yeah, root equals tree node with self.nodelistCounter as its value, except we need to cast it as an int. Okay, and then the left subtree will be what we get when we call this again. But we have to increment the counter by 1. Okay, and then we'll increment the counter by 1 again and call this on the right subtree. I feel like, oh, is that actually going to do what I want it to do? I sure hope so. Okay, root.left equals left, and root.right. Ooh, I can just do this. Okay, and then we're going to return root. I think that's it. Oh, God, I hope that's it, because I'm out of time. Or I'm coming upon being out of time soon here. I think that's it. Let's give it a run. So effectively all this is doing is it's doing this first step where we create the root, because we know what it is by looking at it, right? And then it's saying, okay, now go ahead and move on to the next node. And that's the beginning of the left subtree, right? And that this repeats itself like internally, right? And then once we've exhausted the left subtree, we look at the next node, and that's where the right subtree starts. Ooh, so should there be... I think the only thing I'm uncertain about is where do we increment the counter? We might need one right here as well. All right, I think that's it. I wish I could run, well, let's just give it a run and see if it works first. There might be some syntax issues. Oh. Well, that's sure not what I wanted. Yeah, my only concern is where do we do the incrementing? So we lost the 3 part of this subtree, which that's actually not our diagram. Oh boy. Let me think about this for just a sec. Overall, the approach is definitely right here. I think I've just messed something up pretty dramatically in the code. So the root is the tree node that looks like this. And then we increment the counter so we can start the left subtree. Mm-mm. It's just because over here, we do need to return none, but we also need to increment the counter. Because if you hit an X or a none, right, then you still need to add that to the tree, but you also need to like keep moving forward. Ooh. Yeah, list index out of range. Well, that shouldn't happen because we should do this as many times as the list runs, huh? Now I think we're over incrementing. Actually, now that I think about it, we don't need to do these extra counters over here because this is handled by the nodes themselves, right? So like if you hit an X, you increment. If you hit a valid node, you increment. But when you do the recursion, you don't need to increment. So I think this should do us for. Oh, go to debugging if we're being totally honest right now. Oh, that was honestly better. That felt better than getting it right the first time because I could go in and I actually understood what was going on with the code. You know what I mean? That felt great. Okay. Um, Sweet. That's the end of trees for us. I think this is about as optimized as it can be. I can't think of things that would improve here. Um, it's pretty much as good as it gets for this problem, I think. There's definitely other ways to do this. You could talk about like encoding the subtree sizes in a special way if you wanted to do that, which might make this a little bit more like intuitive. But I think this is a great way to do it. And I think we're going to call it there because I got to get over to the GBM room where we're going to talk more about trees. So see you there if you can join us. And have a great night. See y'all maybe tomorrow at 7 p.m. for another one.